Annualized and continuity equations, very powerful tool for solving many fluid problems. So we have discussed about venture meter. So the purpose of venture meter is to find out the rate of flow of fluid through pipes, and the principle involved by including cross-section area, a pressure difference is created. By measuring pressure difference, so one can find out discharge through the pipeline. So the included angles, we have a convergent cone, divergent cone, etc. 21 degrees for convergent cone and divergent cone around 5 degrees. The cavitation, when pressure is less than vapor pressure at the throat, so the liquid vaporizes and there is a chance of formation of cavity. Due to that, the pipe surface are damaged, and to avoid cavitation, for no cavitation, the diameter at the throat approximately equal to 0.5 times the diameter of the inlet section. The discharge, the same equation as you know. CD represents quotient of discharge 0.98. CD A1, A2, areas at section 1 and section 2, and square root 2GH all divided by square root of A1 square minus A2 square. H is equal to X into S2 by S1 minus 1. S2 is specific gravity of man-made liquid. X is the displacement of the mercury. S1 is the specific gravity of the liquid or fluid, anything, which is equal to pressure difference between 2 points when the horizontal venture meter is in connected to the horizontal pipe. The data minutes Z1 is equal to Z2. Inclined venture meter, so when the pipeline is inclined, so Z1 is not equal to Z2. So only difference is we have a piezometric heads here, P1 by W plus Z1 minus P2 by W plus Z2, which is equal to H is equal to X into S2 by S1 minus 1. So this is venture meter we have discussed yesterday. R5 meter, the quotient of discharge for venture meter is 0.98, whereas for R5 meter it is 0.6 to 0.7. The losses are more as there is a sudden change in cross-section area. We have a gradual convergent and gradual divergent. For venture meter requires more space, whereas venture meter requires less space and it is a cheaper arrangement. The principle is same. By reducing the cross-section area, a pressure difference is created. By measuring pressure difference, one can find out the discharge which is flowing through the pipe. The diameter at point 2 is 0.5 times G1. V0 contract is the point at which jet has the smallest cross-section area. So the same equations, CD A1 A2 square root 2GH by square root of A1 square minus A2 square. Q actually Q critical is quotient of discharge. The CD value is 0.6 to 0.7 and manometric head H is equal to X into S2 by S1 minus 1, same. Z1 equal to Z2 when it is horizontal, and we have a piezometric head difference for other than horizontal position of R5 meter. R5 meter also have discussed. If you see here, there is a sudden change in cross-section area. R5 meter means R5 plate placed here with a opening. So there is a sudden change in cross-section area, and this point at which the jet has minimum cross-section area, this point is called V0 contractor. This happens at a distance of half the diameter. This is the R5 here, diameter is, let us say, D. So this you can expect at a distance of half the diameter of the R5s. Petard tube, another instrument, but this instrument is used for finding out the velocity of the water. And the principle is by reducing the velocity to 0. So when the velocity is 0, it is called stagnation point. Point is the point at which the pressure, the velocity is 0. Stagnation point is the point at which the velocity is 0. And the stagnation pressure head is the sum of static head plus dynamic head. And V actual is equal to, C is the Petard tube constant, maybe around 0.6 to 0.7, square root of 2GH, where H is the dynamic head. H is dynamic head here. And you can also use connect venture meters. H is equal to X into S2 by S1 minus 1. Or V actual, this is a quotient of Petard tube constant, which is equal to V actual by V theoretical. V theoretical is square root 2GH. This is the Petard tube we had discussed yesterday, and this H is a dynamic head, and this is a static head, and total head is also called stagnation pressure head. and as the velocity is reduced to 0, so this is the stagnation point at which the velocity is made equal to 0. And these are the problems here. An R-phase meter with R-phase diameter 0.15 meter is inserted in a pipe of 30 centimeter diameter. We have a 30 centimeter diameter pipe in which R-phase meter is introduced so that the R-phase diameter is 0.15. So here diameter D1 is 15 and diameter D2 is 30. The pressure difference measured by mercury oil differential manometer on the two sides of R-phase meter gives a reading of 40 centimeters here. So this is equal to X here. So when D1 is equal to 15 and D2 is equal to 30, you can get A1, A2 areas at section 1 and section 2. And when H is equal to 40, so 40 is centimeters of mercury. So this is 40 here and S2 by S1. So the mercury specific gravity is 13.6. And this is oil here, so this is oil is 0.8, 13.6 by 0.8 minus 1. So this is equal to 640 centimeters. So the H value is 640 centimeters and we have A1, A2 here. And the CD is 0.62 it has given. So the equation for finding out R-phase meter, this is important for object type. It has given in the GATE examination also. We will come to those questions in a short while. So Q is equal to CD, A1, A2. Square root of 2GH, A1 square minus A2 square, square root. So you see the quotient of discharge 0.62 and A1 will have 166.7 and 706.85 and A1 values are known and G is 981 centimeters per second square or 9.81 meters per second square and H is 640 centimeters. So based on that we can find out the equation either in centimeter cube per second or meter cube per second. Q and value of H is 640 and A1 value is A2 is there and G is there and you can easily get the value of Q with this equation. The other problem, a 20 centimeters by 10 centimeters Winchester meter. So normally while seeing a 20 by 10, some of the students they are taking 20 by 10 is the area at one section. And they are taking A1 is equal to 20 into 10 and they are searching for A2. But 20 by 10 centimeter means, so the diameter at the inlet is 20 and 10 centimeters is the diameter at the throat. So it has given indirectly both the diameters. 20 by 10 centimeter means the diameter at the inlet is 20 and the diameter at the throat is 10 centimeters. So the pipeline carrying oil of specific gravity, this is 0.8 here, let us see. Oil of specific gravity 0.8. The difference in elevation of the throat section and the entrance section of the Winchester meter is 0.5 meters again. Oh, this is also. So the difference in elevation of entrance section, oh this is 0.5 only. Okay. Is this is the difference in elevation here 0.5 meters and differential each tube Winchester meter shows a gauge reference of 40 centimeters here. Calculate the discharge of oil and the pressure between entrance section and throat section. Take CD is equal to 0.92. So the Winchester meter is not horizontal. If you see here, the difference in elevation of throat section and entrance section, that means if you take a datum Z1 for section 1 and Z2 for the section 2, the difference in elevation means Z1 minus Z2. He has given Z1 minus Z2 is equal to 0.5. Or you can take Z1 is equal to 0 and Z2 is equal to 0.5. The difference in elevation means he means to say that the datum, the Z1 minus Z2, so Z1 minus Z2 is equal to 0.5 meters. The differential U-tube intermeter shows a gauge reference 40 centimeters. It has asked to find out discharge of oil and also pressure between entrance section and throat section. D1 is equal to 20 centimeters and D2 is equal to 10 centimeters. So A1 is equal to 314.16 square centimeters. And based on 20 centimeters, you can find out the area. And based on D2, pi D1 square by 4 and pi D2 square by 4. And 8 is equal to 78.5 square centimeters. The value of H, because it is the ventrimeter is not horizontal, Z1 is not equal to Z2. So you need to take this equation P1 by W plus Z1 minus P2 by W plus Z2. So this is the difference in piezometric head when the ventrimeter is not in horizontal, when the ventrimeter is inclined. So you need to take this equation P1 by W plus Z1 minus P2 by W plus Z2, which is equal to H is equal to X into S2 S1 minus 1. So the mercury displacement is 40 centimeters, you can convert to 0.4 here. 0.4 meters, so 0.4 into 13.6 by 0.8 minus 1. So S2 by S1, S2 by S1 minus 1, which is equal to 6.4 meters. So this 6.4 meters is equal to P1 by W plus Z1 minus P2 by W plus Z2. And P1 by W and P2 by W here and Z1. So the total Z1 minus Z2 is 0.5. Or you can take Z1 is equal to 0 and Z2 is equal to 0.5. So Z1 is 0 and Z2 is 0.5 as there is elevation difference. So P1 by W minus P2 by W is equal to 6.9 meters. So he has asked you to find out the difference of pressure head. And pressure between entrance section and throat section, that is P1 by W minus P2 by W 6.9 meters. And find out the discharge here. So Q is equal to CD Q is equal to CD is the quotient of discharge. He has given 0.92. So the quotient of discharge for ventrimeter it is around 0.95. And the quotient of discharge for orifice meter is around 0.6 to 0.7 or around 0.65. Right? Remember that. Sometimes you may not give the value of CD, you can assume 0.98 or 0.95, depends on the requirement. So here he has given CD is equal to 0.92 and A1, A2. So D1 is equal to 20 and D2 is equal to 10. So you can find out, we have the values of A1, A2 and H is equal to 6.4. Sometimes some students are taking 6.9. 6.9 is different. 6.9 is the difference between pressure heads. And this H is the venturi head. So which is equal to 0.4 into S2 S1 minus 1. So this is equal to 6.4 meter. You need to give the value of only 6.4 here or 640. So 2G 9.81, this is 6.4 and A1, A2 are known. So you can find out the discharge with the help of this equation. These two problems are very important. Definitely there is a great question on that. Even Petard tube constant P is equal to C into square root 2GH. All the three final equations are very important. Definitely the gate examination he is touching one or two problems on applications of Bernoulli's equation. We will come to that in the problems. This also we have discussed yesterday, the fluid dynamics, and we will be going to short notes object type questions straight away. And before that, the fluid dynamics, as you know, will be concentrating on forces. We have a body force, surface force and line force. Body force is proportional to volume, surface force is proportional to area, and line force is proportional to length. The forces are, we have a gravity force due to weight of the fluid, pressure force due to pressure difference between 2 points, and viscosity is due to real property of the fluid or due to cohesion, and turbulence force is due to formation of eddies, and compressibility is due to elastic behavior of the fluid, and the surface tension due to cohesive property of the fluid. And we have Euler's equation of motion. Euler's equation of motion will consider gravity force and pressure force. And just I am refreshing the yesterday discussion in a short time. Euler's equation of motion is gravity force and pressure force, and the Navier-Stokes equation is, if you consider the forces, gravity force and pressure force and viscous force, you'll be getting a Navier-Stokes equation, and Reynolds equation of motion is the need to consider gravity force, pressure force, and force due to viscosity and turbulence. That is Reynolds equation of motion, and integration of Euler's equation is Reynolds equation. So you can get an Euler's equation by taking gravity force and pressure force, and force is equal to mass into acceleration, and the force, the sum of forces is equal to mass into acceleration, and Newton's equation of motion. From that you can take forces here and also mass into acceleration. That is resulting in integration of Euler's equation, and the integration of that is Reynolds equation. The ideal fluid, ideal fluid, as you know, the fluid has no viscosity, no surface tension, and incompressible. So for steady rotational flow of an incompressible fluid, the total energy at any point is constant. That is the fundamental definition of the Reynolds equation for steady. These are the assumptions while making Reynolds equation. So for steady rotational flow of an incompressible fluid, the total energy at any point is constant. So P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2. This is, as you know, pressure head. P1 by W is pressure head, velocity head, and datum head. Pressure head at point 2, velocity head and datum head. I will be writing straight away in the problems. So because you might have, followed the discussion yesterday, and I might have seen these topics on our own, so that it will be easy for us to move on the objective questions in a smoothly. So real fluid, when if you consider the losses, when there is a flow from 1 to 2, obviously there are losses here. The loss here we have considered when the flow is from 1 to 2 on this side. So HL is the loss of head between points 1 and 2, and these are all total head. Total head is the sum of pressure head, velocity head, and datum head. Total head at point 1 is equal to total head at point 2, which is pressure head, velocity head, and datum head. So when the total head at 1 is more than total head at 2, so we can have when the flow is from 1 to 2, in other words, when the total head at point 1 is total head at, more than total head at point 2, so we can take HL here. HL is the loss of head. Finally, total head at 1 is equal to total head at 2, even by considering losses here. Real fluid when you consider the viscosity, etc. This is the Reynolds equation, streamline we have discussed, and these are the steps for finding out Reynolds equation, and the problem we had discussed yesterday. And the other one is Newton's equation of motion. F is equal to ma. So F is force, which is equal to mass into acceleration, and momentum equation, which is F is equal to d of mv by dt. That is change of momentum with reference to time. So d of mv is a change of momentum here. Mass into velocity is a momentum change into d of mv, and dt. Rate of change of momentum is force here, which is momentum equation, and which is also equal to rho q if you make the quantity of water as discharge, constant. So q is the discharge, quantity of water flowing through the pipe per meter cube per second unit, and rho is the mass density. So rho into q, so F is equal to rho into q into V2 minus V1. That is generalized momentum equation. And also we have impulse momentum equation. When you take this dt onto this side, and as acceleration is rate of change of velocity, I have taken dv by dt. As mass is constant, you can take inside to get momentum equation is a modified form of Newton's equation of motion, and impulse momentum equation is a modified form of Newton's equation of motion. There are not new equations. The basic equation for getting these two is Newton's equation of motion. The other one is impulse momentum equation is f of dt is equal to d of mv. So f of dt is, if you take this dt to this side, so this is f of dt is equal to d of mv. So f of dt is force in a time dt. This is also called impulse. Force in a time dt is called also impulse. And momentum equation, change of momentum is d of mv, which is equal to f of dt. So f of dt is equal to d of mv. So the force in a time dt, which is equal to change of momentum, d of mv. So we have taken up the forces on the bend, and anyway we have a gate also. I mean, in the gate examination has again a problem on bend also. So we'll be discussing that in while doing gate questions. And it is required to find out. So we have the three forces here. So one is the pressure force here, and we have the force by the fluid on the bend, and we have the weight here. These three are the pressure forces here, and the sum of the forces is equal to rho q into fx. If it is fx, which is equal to rho q into vdx minus v1y, and we have discussed yesterday fx fy. So you can find out fx here, fy here. This is theta. Fx here, fy here. P1 A1 P2 A2 cos theta, sin theta. This is also sin theta, and rho q v2 cos theta minus v1. I need to use appropriate this signs and also the resolve the components in the perfect direction with the proper signatures, and resultant is equal to square root of fx square plus fy square. That is resultant. Then go to objective questions. So these objective questions will cover both Benol's equation and applications of Benol's equations and also momentum equation. So we have completed two chapters. In addition to the earlier chapters, fluid properties, fluid pressure, hydrostatic forces, and fluid statics, pressure chapter, etc. In addition to those chapters, we have also completed fluid dynamics, including Benol's equation, which includes Benol's equation, and also momentum equation, and also applications of Benol's equation. So all the three chapters of objective questions put together into the series of objective questions, which involves Benol's equation, momentum equation, and venturometer, RFS, petard tube, etc. So this is first one is the Benol's equation definition. In the year 1994 he has given. So Benol's equation can be applied between any two points on a streamline for a rotational flow field. So it can be applied between any 2 points, absolutely no problem. And the answer is true. The second problem, water flows through a vertical contraction. So this is contraction of a pipe of diameter, from a pipe of diameter is d here. On one side the diameter is d, other side the diameter is d by 2. So it has given d and d by 2. So water flows through a vertical contraction from a pipe of diameter d. So we have a d here, there is a contraction, and diameter here is d by 2. So that means area here is pi square by 4, and area here is the diameter here is d by 2. The flow velocity at the inlet. So when q is equal to a1 v1 is equal to a2 v2, q is equal to a1 v1 is equal to a2 v2. So we can substitute the values here. So we can substitute the values here, and a1 v1 is equal to a2 v2. So q is equal to a1 v1 is equal to a2 v2. So a1 is pi square by 4 into v1, and a2 is pi d by 2 whole square by 4. So the flow velocity at the inlet of the contraction is 2 meters per second. So it has given the flow is 2 meters per second. So you can take it is 2 meters per second, and we can get the relation between v1 and v2 because we have the value of a1. So a1 is pi square by 4 and a2 is diameter is d by 2. So you can get a1 v1 and a2 v2. In other words, a1 v1 is equal to a2 v2. So a1 is known and a2 is known. You can get the relation between v1 and v2. So now V2 is equal to 4 times V1. So that means we have used the now continuity equation. So for any solution, if you use a continuity equation, Bernoulli's equation, that solves many fluid flow. So A1 V1 is equal to A2 V2 and substitute A1 and A2 values, and so that we can get V2 is equal to 4 V1. So the first solution is V2 is equal to 4 V1 and then apply Bernoulli's equation. So Bernoulli's equation is P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2. Z2. So here what is Z1 here? We can take a datum here. We can take a datum here. Z1 is 0 and Z2 is 2 meters. So this is the elevation difference. In other words, Z2 minus Z1 is 2 here. So Z1 is the datum. This is a vertical position, the pipe. So the Z1 here is 0. If you take a datum here, Z1 is 0, and here if you take the value, Z2 is 2 meters here. So now take P1 by W. So he has given the flow velocity at the inlet, but the contraction is 2 meters per second and the pressure is 200. So we can have the value 200 is the pressure, 200 kilonewton per meter square is the pressure P1, and the pressure at the exit of the contraction will be. So he has asked to find out P2 here. So we have used the continuity equation. V2 is equal to 4 times V1. So V2 is equal to 4 times V1. And V1 is 2 here. So the velocity of the inlet is 2. Then what is V2? V2 is equal to 4 into V1. So when V1 is equal to 2, V2 is equal to 8 meters per second. So that means we have the value of V1, V2, Z1, Z2 and also P1. Only unknown is P2. Okay, P1 by W. So P1 is 200 kilonewton per meter square by W. W is 9.81 kilonewton per meter cube. So that is P1 by W1. And V square by 2Z. V is velocity of the inlet is 2 meters here. So that is 2 square by 2 into G, 9.81. And Z1 is 0. So here Z1 is 0 here, which is equal to P2 by W. P2 is not known. And W is 9.81 kilonewton per meter cube, and V2 square by 2Z. So because V2 is equal to 4 times V1, V2 is equal to 4 times V1, so V1 is 2, so V2 is equal to 4 into 2, that means V2 is equal to 8 meters per second. So V2 square by 2Z is 8 square by 2 into 9.81, and Z2 is 2 meters here. So the datum head for 1 is 0, datum head for 2 is 2 meters here, so this is 2. And we have all the values are known except the value of P2, and the P2 is equal to 150 kilonewton per meter square. So the answer is C. So just you have applied continuity equation, Bernoulli's equation for getting the pressure at unknown section. And third problem. Consider the study encompass of rotational flow. So that is Bernoulli's equation. And he is saying that you can apply Bernoulli's equation. Consider study incompressible and irrotational flow through a reducer in a horizontal pipe. And suppose if you see here, he has given a reducer. So the pipe cross section is reducing. So it is 20 centimeters here, reduced from 20 to 10. So here this is a diameter here is 20 centimeters here, and diameter here is 10. The pressure in the 20 centimeters pipe. This is the pressure here, 20 centimeters pipe. He has given pressure in the 20 centimeters pipe is 150 kilopascals, kilonewton per meter square. And the fluid has a vapor pressure of 50 kg per kilopascals here. So the velocity, the pressure here at section 2 is 50 kilopascals. And a specific weight of 5 kilonewton per meter cube. Specific weight of 5 kilonewton per meter cube, and negative frictional losses. He has asked to find out the maximum discharge in meter cube per second that can pass through this flow here. He has not given V1 and V2. So the first equation is A1 V1. So this is a specific weight. Specific weight W is equal to rho into Z, 5000 Newton per meter cube. So this is 5 kilonewton means 5000 Newton per 5 kilonewton per meter cube is 5000 Newton per meter cube. So we have A1 V1 is equal to A2 V2. And A1 we can find out with the help of pi by 4 D1 square. So pi by 4 D1 square, pi by 4 into D1 square is 20 square. And A2 is pi by 4 D2 square, D2 is 10 here. So we have a D1 and D2 values. He has directly taken 20 by 10. So V2 is equal to A1 V1 by A2. So pi by 4 cancel, and 20 square by 20 by 10 whole square. So in other words, V2 is equal to 4 times V1. Missed అక్కడ రెడీ ఉంటే చెప్పానండి నేను క్లాస్లో అయితే 5 నిమిషాలు అవుతాము 7:05 సరే. So here A1 V1 is equal to A2 V2. So V2 is equal to 20 by 10 D2 by D1 whole square into V1. So we'll be getting V2 is equal to 4 times V1. And you can apply Bernoulli's equation. You can apply Bernoulli's equation here. So Bernoulli's equation is P1 square, P1 by W plus V1 square by 2G plus Z1, which is equal to P2 by W plus V2 square by 2G plus Z2. And as this is horizontal, the pipe is horizontal, Z1 is equal to Z2. So you need not take Z1 and Z2 because Z1 is equal to Z2. So this is P1 by W plus V1 square by 2Z, which is equal to P2 by W plus V2 square by 2Z. So the pressure P1 is 150. So 150 kilopascals means 150 to 10 power 3 pascals. Kilopascals is kilonewton per meter square. So 150 to 10 power 3, 150 meter square by 5000. So 5000 is the basic weight. So it has given 5 kilonewton per meter cube. So this is 5000 newton per meter cube P1 by W. V1 square by 2Z, V1 is not known. And this is P2 by W. P2 is 50 kilopascals here, 50 into 10 power cube by 5000 plus V2 square by 2Z. So you can substitute the V2 is equal to 4 times V1. So you can substitute V2 4 times V1 here. And this equation is, this is 30 plus V1 square by 2Z. This is 10 plus V2 square by 2Z. In place of V2 square by 2Z, you can take 16 V1 square by 2Z so that you can find out V1. So this is the value V1 here, and you can get Q is equal to A1 V1. So A1 is pi by 4 into 0.2 if it is in meters. So pi by 4 into 0.2 and V1 is this value, so that the equation is 0.16. The answer is 0.16. So now Q is equal to A1 V1, which is equal to 0.16. And Navier-Stokes equation represents the conservation of. So Navier-Stokes equation, as you know, and I told you there are 3 equations. One is Ayer's equation, Navier-Stokes equation, and also Reynolds equation. So this is all based on momentum. Navier-Stokes equation represents the conservation of momentum. So the continuity equation is based on law of conservation of mass. Mass can be neither destroyed and Navier-Stokes equation represents the conservation of momentum, that is D. And in a venturometer, the next question, in a venturometer, the angle of diverging section is more than that of converging section. So number of times during discussion, the convergent cone, the angle of convergent cone is around 21 degrees, 20 plus or minus 1, and divergent cone is between 5 to 15 or around 5 degrees here. So the convergent cone include angle is always more than divergent cone include angle. So that may the angle of divergent cone is more, which is not correct. It is a false statement here. So the angle of divergent cone is kept small to reduce the possibility of flow separation. Due to this, the angle of converging section is more as compared to its diverging section. Okay. A short break here. There is some important inauguration. I will be back in 5 minutes, maximum 10 minutes, and I will continue from now. The time is 11:05. I will be back by 11:15, and from 11:15 I will continue up to 12:30 without any gap. So short break. Will be completing the very can continue up to 12:30. Sorry for the interruption, and I'll be back. Yes, my dear student friends. The next question. Venture meter of 20 centimeters throat diameter is used to measure the velocity of water in a horizontal pipe of 40 mm diameter. If the pressure difference between the pipe and throat section is found to be 30 kilopascals, then neglecting velocities, frictional losses, the flow velocity is. So here, once again, this is another simple problem. This is venture meter, and we have equations here. Q is equal to A1, V1 is equal to A2, V2. So he has given a diameter 40 mm here and 20 mm here, 40 mm here and 20 mm here. So substitute the values V1, V2, and V1 and V2 are not known, so V2 is equal to 4V1. Then apply Bernoulli's equation, P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2. So here P1 minus P2 by W is equal to V2 square minus V1 square by 2Z. So we have the velocity V2 is equal to 4V1. You can substitute the value here, and this is known here. P1 minus P2 by W is known. He has given, you see here, the pressure difference between the pipe and throat. So this is the pipe, this is a pipe P1 here, then this is throat here. The pressure difference between P1 and P2, he has cited given P1 minus P2. So that is, he has given 30 kilopascals. So 30 into 10 power 3 pascals, 30 Newton per meter square by specific weight. So based on that, you can find out the velocity. P1 by P2 is known, and V2 and V1 you can convert to V1 here because V2 is equal to 4V1, so that you can find out V1 is equal to 2 meters per second. Simple calculations. No, nothing complicated here. One, use continuity equation and Bernoulli's equation. The Z1 is equal to Z2. If it is horizontal, as long as it is horizontal, you can take Z1 is equal to Z2. So Z1 you can neglect if it is horizontal. Z1 and Z2 you can neglect if it is horizontal. Then this is Bernoulli's equation. Yeah, Bernoulli's equation represents the definition itself. It is energy, not the force, not the momentum, not the moment of momentum. It is energy straight away here. Energy is at any point in the flow field and is obtained by integrating the Euler's equation. Very clear. So it is energy at any point in the flow field and is obtained by integrating the Euler's equation. Integrating the Euler's equation. Second one. The Bernoulli's equation is applicable between any 2 points in a flow field only when the flow is steady, incompressible and irrotational. So the D answer is valid here. This is not tiled. This is D. The flow is steady, incompressible and irrotational. So the answer, the Bernoulli's equation applicable of because of 3 assumptions here. Steady, the petard static tube. So it is titled, we have 3 here. Petard tube. Petard tube measures stagnation at total pressure head. Total pressure is a sum of static and dynamic. And the static tube measures static pressure head. And petard static tube is a combination of both petard and static tube, which measures directly the difference between total and static pressure. So this is the answer is D here. The most appropriate governing equation of ideal fluid flow or Euler's equation. Ideal flow means Euler's equation. So Euler's equation of motion consists of pressure, gravity forces. Navier-Stokes equation consists of pressure, gravity and viscous force. Reynolds equation consists of pressure, gravity, viscous and turbulent forces. Ideal fluid does not possess viscosity. Does not possess viscosity. So the answer is A for question 2. And second one. If the velocity distribution is rectangular, the kinetic energy correction factor is. Answer is equal to unity. So this is the theory here behind that. Velocity distribution is parabolic. If flow is laminar, that means for the laminar flow, the kinetic energy correction factor is 2. This is additional information with the help of the AS coaching material and also fluid mechanics and hydraulic machines and all. So the velocity distribution in parabolic, if flow is laminar, if it is laminar, for which kinetic energy correction factor is 2. If it is turbulent, the flow is turbulent, the kinetic energy correction factor is 1.01 to 1.2. But if the velocity distribution is rectangle, so it has given velocity distribution rectangular. So in that case, the kinetic energy correction factor is equal to 1. So the answer is D. You can also remember this parabolic and laminar flow. Then the kinetic energy correction factor is 2, and it is rectangle. If it is turbulent, then correction factor is 1.01 to 1.2. The range of quotient of discharge, range of quotient of discharge of a Winchell meter is. .5 to 0.6, 0.7 to 0.8, and 0.6 to 0.7. So the quotient of discharge for the Winchell meter always it is 0.95 to nearing 1. The losses are less. So because the Winchell meter has both converging and diverging cones, and hence the losses are minimum, the quotient of discharge is almost near to 1. It is 0.95 to 0.99. In R-phase meter, we have a solid plate, sudden change in cross-section area, the losses are more. The quotient of discharge will be 0.6 to 0.7 or 0.62 to 0.67. In nozzle meter, only converging cone here, no diverging cone, losses are more, and the quotient of discharge for nozzle meter is 0.7 to 0.8. Remember these two also in addition to 0.95 to 0.99 for Winchell meter. So the answer is D. If the discharge to two orifices, orifice means opening, just the opening provided in the side of the tank through which fluid is flowing. So we have a place at 2 depths here. So this is the head here. So place at 2 depths, a head here 200 and 800 in water are equal. The ratio of diameters is. So we have the equation Q is equal to AB, discharge equation, which is pi by 4 d square into square root h, and pi by 4 is a constant, so proportional d square square root h, and Q1 is equal to Q2, the same discharge, and he has also find out ratio of diameters. He has given depths here, heads he has given, so d1 square square root h1 and d2 square square root h2. So you can get the relation here, d1 by d2 square is equal to square root h2 h1, and which is equal to 0.8 and 0.2 he has given. So this is d1 by d2 square, 0.8 by 0.2, it will be 2:1, and d1 by dt is equal to square root 2:1. So this is a simple equation. With the help of just a discharge equation, we can get the answer. Square root 2 is equal to 1, and provided it should be at CL. 6. Bernoulli's equation is the equation of conservation of energy. So because all these are all energies here. The Bernoulli's equation means all energies here. Bernoulli's equation states that the net mechanical energy remains a constant along a streamline. Bernoulli's equation states the net mechanical energy remains a constant along a streamline. So therefore this is an equation of conservation of energy. So 6 is C. Petard tube used to measure answer is C. You can find out total pressure or stagnation pressure. Total pressure or stagnation pressure is equal to static pressure plus dynamic pressure. And petard tube, the purpose of that you can get the stagnation pressure. So water flows steadily down in a vertical pipe of a constant cross section, neglecting friction according to Bernoulli's equation. And suppose if you see here the water is flowing down, the water is flowing down. And we apply Bernoulli's equation between sections 1 and 2, P1 by gamma plus V1 square by 2G plus Z1 is equal to P2 by gamma plus V2 square by 2G plus Z2. And he has given the same diameter means areas are same. When areas are same, if you take Q is equal to A1, V1 is equal to A2, V2, A1, V1 is equal to A2, V2, then V1 is equal to V2. So now, in the equation, so as V1 is equal to V2, we can cancel V1 square by 2Z and V2 square by 2Z. So we have a P1 by gamma plus Z1 is equal to P2 by gamma plus Z2. Yeah, as water flows down, suppose if you take Z1 here, and Z2 here, as water flows down, so okay, you have the value here. So Z decreases here, as Z is less here, as you are coming down, if you take a datum here, so this is Z1 some value and Z2 some value, if you come down, we are coming down, the Z is decreases here, as Z is decreases, then what happens to pressure? The pressure increases in the downward direction. As you know, pressure always increases in the downward direction. So answer is C here. If Z decreases, then pressure increases. So this is answer is D here. Answer is C. Pressure decreases with height. Answer is C. HC. 9. So if you see here, this is V square by 2 plus GZ plus square root dP by rho. So in the Bernoulli's equation, we assume that the fluid is incompressible. But in this equation, if you see here, integral dP by rho, so this is also they have considered. So that means rho is not constant. If rho is not constant, then it is a compressible fluid. If the rho is constant, you can take outside and this is not having any effect. It is an integral dP by rho. So this is a compressible fluid. So then steady, frictionless and compressible fluid is the answer for this equation. So it is not incompressible. So in all the three, it is incompressible, but it is only compressible because the mass density is not constant. So this is 9, the answer is A. Since the pressure energy term is in differential form, the equation is valid in the case of compressive flow as well. 10C. So if you see here, the kinetic energy correction factor for a fully developed laminar flow through pipes, then the value of kinetic energy correction factor. So the kinetic, instead of remembering this entire value, so the kinetic energy correction factor value is 2. So you can straight away remember this value and you can take the value of 2. So the answer 10, the answer is C. In a Bernoulli's equation, used in pipe flow, each term represents. This is no doubt energy per unit weight. So 11 is answer A. P by W plus V square plus Z. P by W plus V square by 2G plus Z is constant. The common used in Bernoulli's equation in pipe flow, unit of each term in the above equation is energy per unit weight. The question 12 here. A frictionless fluid of density rho flows through a bent pipe as shown below. So the fluid is taking this path here and coming down as shown below. If A is a cross-section area and V is the velocity of the flow, the force exerted on segment 1, 2 of the pipe. So he is asking the force in x and y directions are. So you can find out Fx and Fy. So this is the solution here. Mass density of the fluid and cross-section area, velocity is known. Applying momentum equation. The problem is under momentum equation. So sigma Fx is equal to mq into v2x minus v1x. And velocity here, so v2, so this is only x direction. The velocity here is v1 is equal to v and v2 is also equal to v. So same velocity here he has given. It is in x direction, so this v and v are same, so Fx is equal to 0. In y direction, if you see here, so this is v2x minus v1x, this is v2y minus v1y. So this is perfectly in x direction, there is no component in the y direction. So v2y, you cannot get v2y and you cannot get v1y. So v2y minus v1y is also equal to 0. So Fx is equal to 0 and Fy is equal to 0. So the answer is the C. 13. Group 1 gives a list of devices and group 2 gives a list of uses. So the petard tube, manometer, venturimeter and anemometer. Suppose if you see here petard tube measuring the velocity, so that means the 2 answer is correct. So maybe between C and B. And manometer, so manometer measuring pressure, manometer measuring pressure. So it should be 1. So B and C both are having 1. So 2, 1, 2, 1 both are correct. So that means either maybe B or C. And R, venturimeter. So venturimeter measuring discharge. So this R should be 4. R should be 4. Here R is 3 and this should be 4. So that means the answer is C. And S is anemometer. Anemometer is also measuring air and gas viscosity. So this answer C is correct. So petard tube measuring velocity of the flow, manometer measuring discharge. Manometer measuring pressure and venturimeter measuring discharge and anemometer measuring air and gas velocity. So C, answer C is correct. Answer C. So same thing. So 14. The circular water pipes. These are all gate problems. The circular water pipes shown in the sketch are flowing full. The velocity flow in meters per second in the branch pipe are. So here we have the velocity here V1 6 meters per second and the velocity here 5 meters per second. The velocity has also find out the velocity here and the diameter here 4 meters and diameter here is 4 meters and the diameter here is 2 meters. So it is it has given velocities and diameters. So you can use a discharge equation. So at junction J, inflow is equal to outflow. So inflow is equal to here area and the velocity. So area is AP, area here is AP and the velocity here is VP, which is equal to outflow. Outflow means from here to here and from here to here. So this is equal to area here is KQ and the velocity here is VQ, and the area here is AR, and the velocity here is VR. So simple discharge equation, in other words, this is Q1 is equal to Q2 plus Q3. Q is equal to area and velocity. So here this is area and this is velocity, area velocity and area velocity. So area is equal to pi by 4. So you have a pi by 4 d square, pi by 4 d square, pi by 4 d square. You can cancel pi by 4 on both sides. So dp square, the diameter has given 4 square, and the velocity of the pipe here, here at point P is 6 here, it has given, and dq, the diameter is also same here, 4 square, and the velocity here is 5 plus 2 square, the diameter is 2 here, diameter square is 2 square, and into B here, so B is, the velocity is not known. So you have all the values here, this is 90, this is 80, plus 4B, 4B is 16, and B is equal to 4 meters per second. So the answer is B. So the other problem, 15, group 1 lists a few devices while group 2 provides information about their uses. Match the devices with their corresponding use. So first we are strong in getting petard tube. So petard tube is for finding out fluid velocity. So that means petard tube is R here and this 2 is correct. R versus 2. Suppose if you see here R and we have only answer, that is 2 here. Instead of wasting time on other aspects, because you are confident that the petard tube is for finding out fluid velocity at a specific point in the flow stream, so you can straight away go for this answer D. So no doubt animator P, wind speed, and Q, hygrometer for water vapor content, and tensionometer for capillary potential. But you are confident that petard tube for measuring fluid velocity. So the answer R is 100% true for 2. So R is equal to 2 only for this equation. So the answer is D. Shortcut. Also, we know that the petard tube is used to measure the velocity of the fluid at a specific point in the flow. With this understanding, the matching is R2. So only option D is satisfying this. Simple way of taking up. Bernoulli's equation is applicable for inviscid and incompressible. So the answer is C, 16C. So only for ideal fluid is inviscous. So absolutely there is no problem. So these are the 2 marks question in the GATE examination. First question. A tank containing water has 2 orifices of the same size at depth of 40 centimeters and 90 centimeters. The ratio of the discharge through these orifices are. A tank containing water has 2 orifices of the same size. So he has given the depth here 40 and 9 centimeters. The ratio of the discharges through the orifices. So here, as you know, Q1 is equal to A1 V1 and Q2 is equal to A2 V2. And he has given 2 orifices of same size. 2 orifices of same size, the diameter is same. So when the diameter is same, A1 is equal to A2. So then Q1 is equal to V1 and Q2 is equal to V2. A1, A2 are same. Q1 V1 is equal to A1 V1. Q is equal to A1 V1 is equal to A2 V2. And because A1 is same and A2 is same, so you can take In other words, Q1 is equal to V1 and Q2 is equal to V2. So Q1 by Q2, A1 V1 by A2 V2. So we can cancel A1 and A2 here, and so that we have V1 and V2. So the velocity is square root 2gh. So this is square root 2gh1. So Q1 square root 2gh1 and V2 square root 2gh2. 2g cancel, and it is the square root of h1 by h2. So Q1 by Q2 is proportional to square root of h1 by h2. And h1 we have 40 centimeters and 0.4 meters, and h2 we have 90 centimeters or 9.9 meters, and the answer is 2 by 3 or 2:3. So the answer is B. The discharge coefficient CD of an orifice meter smaller than, the answer is straight away smaller than CD of inch meter here. Equal to CD is not correct, greater than 1 is not correct, greater than CD is not correct, 1 is smaller. The B, answer is B here, smaller than the CD of inch meter. So the answer is B here, and this is a general discussion. RFS meter has neither converging nor diverging cone, hence losses are more. The coefficient of discharge will be 0.62 to 0.67. Wincher meter has both converging and diverging cones inside through which the flow occurs, hence the losses are minimum, hence the coefficient of discharge is more and near to unity for Wincher meter. So the CD of an RFS meter always smaller than CD of a Wincher meter. This is the problem of petard tube. So petard tube is used to measure velocity V in a duct of a gas with the density rho and static pressure P. It is connected to a U-tube manometer containing a liquid of density rho m, the height h is. So this is the petard tube. Number 3. Applying Bernoulli's equation, and instead of that a short cut, kinetic energy of the gas is converted to potential energy of manometer liquid. So we take kinetic energy and pressure energy here. So kinetic energy is half mv square. So m is the mass here, mass density, half mv square here, and rho by g here, half mv square. And this is 1 by 2 v square, kinetic energy. Then the pressure energy here, the density of the mercury into height here. So kinetic energy converted, and so that these two can be equated here. So then H is equal to rho by rho m into v square by 2g. Short form here, you can easily get this. Kinetic energy of the gas is potential energy of a manometer liquid. So half mv square, this is rho v square by 2g, and rho m h here, and rho m is the density of the manometer liquid, and h is the difference here. So h is equal to rho by rho m to v square by 2g. So the answer is A. The answer is A. 4. Fluid flows steadily. Fluid flows steadily through a variable area duct. At section 1, the density is rho 1, cross-section area is A1, and velocity is V1. He has given rho 1, A1, V1, and pressure is P1. And the corresponding values of the at section 2 are rho 2, E2, V2. Rho 2 is the mass density at section 2, and A2 is the area at section 2, and V2 is velocity at section 2, and P2 is the pressure. Then the following relation is satisfied. We have a discharge equation, contained equation. Discharge is contained equation for dimensional flow, for which the assumptions are steady incompressible fluid. So A1 is equal to A2 V2. This is the force here, P1 even force 1, force 2, A1 1, this is discharge, Q1, Q2. This is force. But here, the content equation, the fluid is incompressible. That's assumption we have made for finding out the content equation. Q is equal to A1, V1 is equal to A2, V2. In that we have considered rho is a constant, but when rho is not constant, it will be rho 1 A1 V1 and rho 2 A2 V2. So because he has asked to give the relation between these following relation. So rho 1 A1 V1 equal rho 2 A2 V2. One is C. Answer C is correct. So data shows that the flow is one-dimensional and content equation for one-dimensional compressible flow. It is not incompressible. Compressible flow equation is rho 1 A1 V1 is equal to rho 2 A2 V2. Rho 1 A1 V1 is equal to rho 2 A2 V2. Fine. When a steady jet of water impinges on a stationary inclined plane surface, and if fluid friction is neglected, the resultant force on the plane is normal. So whenever friction is neglected, the tangential component of the force. So when friction is neglected, whatever the tangential component of the force becomes zero. Therefore, only we have only normal. The resultant force is 1 into normal, because the tangential force when friction is neglected, whatever the tangential force which is sliding, which is in line with the surface, when frictional force is not there, the tangential force is 0, then we have only normal force. So the resultant force is normal to the surface. He has given fluid friction is neglected. So when fluid friction is neglected, we have only normal force can be considered, and we can remove and we can neglect the tangential force. So this is answer B, is normal to the surface. Six. A nozzle discharging water under head H has an outlet area A and discharge coefficient CD is equal to 1. Discharge coefficient CD is equal to 1. A vertical plate is acted upon by the fluid force Fj when held across the free jet and by the fluid force Fn when held against the nozzle to stop the flow. So the ratio of Fj by Fn. Fj is the fluid force when the plate is held across the free jet, and the fluid force Fn when held against the nozzle to stop the flow. He has asked to find out the ratio. This CD is equal to 1. The equation for just striking a plane, it is rho AV square, is a famous equation. Mass density into area into velocity square. And because the final velocity is 0, rho A into V2 minus V1, final velocity is 0, so rho AV, rho discharge into V2 minus V1, final velocity is 0, and it will be rho AV square. This is a general equation. So the force by the jet is rho AV square, A is the area of the jet and V is V square, and the application is impact of jet. The momentum equation application for impact of jet, that is the problem in this. We have discussed that on pipe bend. And we have also application for impact of jets. This is the application of that. So the force by the jet on the plate is rho AV square. A is the outlet area of the jet and V is the velocity flow. And now this case is over. And find out Fn. Plate held against the tip of the nozzle. Now it is a normal force. So which is equal to P into A, WHA. W is rho into G. And this is the area here. And what is H? So we have the equation V is equal to square root 2gh. We have the velocity V is equal to square root 2gh and H is equal to V square by 2g. So you can substitute the value of H is equal to V square by 2g, and A is the area and rho g is the WHA, the force, WAH. So H is equal to, you can convert into in the form of velocity, V square by 2g is equal to H, or V is equal to square root 2gh. So you can substitute H in place V square by 2G. So this is rho A, G and G cancelled, and rho A V square, rho A V square by 2, a small a, he has given capital, this is small a, and Fj is rho A V square, and Fn is rho A V square by 2. So the answer is 2 here. Fj by Fn is equal to 2 here. So the answer is D. So for this we need to have some concept of impact of jets, which is there in hydraulic machinery, and some other expert will be taking impact of jet. I will be covering our fluid mechanics, but this is the application for momentum equation. So rho A V square is the force by the jet on the plate. So when there is a reduction in the cross-section area, the water comes out in the form of jet. If you place a plate on that, the entire force by the jet on the plate is rho A V square. And normal force is WHA, this is a normal one, and H you can take V square by 2G, and the ratio is 2. 9. The reading of a differential manometer of a venturimeter placed at 45 degrees to the horizontal is 11 centimeters. If the venturimeter is turned to the horizontal position, the manometer reading will be. So whatever the position we have a venturimeter for the horizontal pipe, obviously the height of rise is same. It should be, the C should be 11 centimeters. Explanation for that. The discharge to a venturimeter is given by the formula, as you know, Q is equal to CD. A1, A2 by square root of A1 square minus A2 square into square root 2GH, where H is venturi head. So X is equal to S2 by S1 minus 1. X is a differential level of manometer fluid, and CD, A1, A2 are the same. Same discharge in all orientations. A1, A2 are same and same discharge in all orientations. The value of X is also same. Even if the venturimeter is turned to the horizontal position from the inclined position, no change in manometer reading. Manometer reading obviously 11 centimeters in the horizontal position also. Provided that A1, A2 are same and CD are same. For both cases, CD are same and A1, A2 must be same. So this is only depends on the value of H. H depends on the value of X here. So this is same manometer will be there, provided all the other values are same for both the position of horizontal, horizontal position or vertical position or inclined position of venturimeter. Next problem. A horizontal water jet with a velocity of 10 meters per second and a cross-section area of 10 mm square strikes a flat plate held normal to the flow direction. The density of water is 1000 kg per meter cube. The total force on the plate due to the jet is. Simple problem. The equation is rho A V square. So velocity of the jet he has given 10 meters per second and cross section area 10 mm square. The density of water is 1000 kg per meter cube. So density has given 1000 kg per meter cube. Area straight away has given 10 mm square, and convert 10 into meter square. 10 into 10 power minus 6 will be getting in meter square. The area of the cross section of the jet is 10 mm square. So 1 mm is 10 power minus 3 meter. So 10 power minus 6 square meters here. So 10 into 10 power minus 6 into 10 whole square is equal 10 whole square is V square. Velocity is 10 meters per second. So 10 square rho A V square. The answer is 1 Newton. So the answer is C here. At 2 points 1 and 2 in a pipeline, okay, it has taken a pipeline and the velocities are V and 2V respectively. Both the points are the same elevation, means it has given Z1 is equal to Z2. The fluid density is rho. The flow can be assumed to be incompressible, inviscid and steady and rotational, all the assumptions. Difference in pressures P1 and P2. Indirectly, he wanted us to use Bernoulli's equation. Velocity is also V and 2V. So take Bernoulli's equation here for the pipes in which the reducing cross-section area. So the velocity here is V and the velocity here is 2V. And the flow is rotational here, there are no losses here. There are no losses here, you can straight away use the Bernoulli's equation for the ideal fluid. For the real fluid, as you know, P1 by W plus V1 square by 2G plus Z1 is equal to Pt by W plus V2 square by 2G plus Z2 plus HL. HL is 0 because there are no losses, you can straight away take the equation for ideal fluid. So for the horizontal pipe, so the pipe is horizontal here, so the datum heads are equal, Z1 is equal to Z2. These pipes are horizontal here, Z1 is equal to Z2 and gamma is equal to rho G, general equation. So when Z1 is equal to Z2, the equation distributed to P1 by W plus V1 square by 2Z is equal to Pt by W plus V2 square by 2Z or gamma. So W or gamma, which is equal to 1 to Z. So then P1 minus P2 by gamma is equal to V2 square minus V1 square by 2Z. So we have V2 is equal to V. When you reduce the cross-section, the velocity will be more, 2 times of that. So this is 2b here, 2b minus 2b square minus v square by 2z. So 3b square by 2z, and if you resolve the, if you simplify this, 1.5 v square by 2z is p1 minus p2 by gamma. So you have also to find out the pressure difference, p1 minus p2, you can take gamma here. So gamma into 1.5 T square by 2z, and this gamma or W is equal to rho into G. So you can take rho G here in place of gamma. Gamma is equal to rho G. So rho G into 1.5 square by G, and G cancel. So this is 1.5 rho V square. So the answer is B here, 1.5 rho V square. So these problems are all 2 marks problems. It may take time for solution, but not a difficult, and you can quickly, if you do the problem, if you remember the equations and the notations and assumptions properly. So the problem 12, water, unit weight of water is 9.87 kilonewton per meter cube, flows with a flow rate of 0.3 meter cube per second. 0.3 meter cube per second is discharge. Flow rate means it is discharge, 0.3 meter cube per second through a pipe AB of 10 meters length. The length of the pipe is 10 meters. Cross-section area is uniform. The end B is above end A. So A is at road level and B is at height level, and the pipe makes an angle of 30 degrees to the horizontal. This is an intelligent question, not a difficult question, but you need to get the datum by using the angle. Datum at point 1 is okay, 0 can take. Datum at point 2, which is high level, it has not given the difference of elevation, but it has given the length of the tube and the angle, so that you can use the sine or cos theta to get the datum here. That is the only change here, but it's not difficult, provided you know. You can get the datum with the help of the length and angle. For a pressure of 12 kilonewton per meter square at the end B, he has asked to find out the pressure at the end A. Simple Bernoulli's equation, but he has not given Z2 directly. Z1 is Z2, datum head not directly. You need to get that with the help of length and angle. Simple equation, he has given the specific weight of water is 9.879 kilonewton per meter cube. The flow rate Q is equal to 0.3 meter cube per second. Length of the pipe AB is equal to 10. He has given the length of the pipe here, from here to here, the length is 10 meters. Length of the pipe, he has given 10 meters. The angle is 30 degrees here. and the discharge is equal to Q is equal to A into A1 V1 or AA VA or is equal to AB VB, the continuity equation. So when it is a uniform cross section of the pipe, the diameters are same. As the diameters are same, the areas are same. When you use the continuity equation, Q is equal to AB or A1 V1 is equal to A2 V2, both the sides the pipe is same, having same diameter. So you can make A is equal to AB and the velocity is VA is equal to VB. So pressure at section 1 he has given 12 kilonewton per meter square. He has also to find out pressure at the other section. Apply Bernoulli's equation. So PA by W plus ZA plus VA square by 2Z is equal to PB by W plus ZB plus VB square by 2Z, and we have a loss of head here. Loss of head HL. We can assume this loss of head HL is equal to 0 because not mentioned anything. If he specifically mentioned because of the assumptions, all the assumptions we can take that the loss of head HL is equal to 0 and VA is equal to VB. Then you apply the Bernoulli's equation here. So when VA is equal to VB, VA and these two will be cancelled and HL is equal to 0, this will be cancelled. Now this is PA by gamma plus ZA is equal to PB by W plus ZB. So this HL is 0 and the velocities as velocity V and VB are equal, these two can be cancelled, and ZA, this is if you take datum here, ZA is also equal to 0. So this is PA by gamma is equal to PB by gamma plus ZB. Then PA is equal to gamma into PB by gamma plus ZB, and in other words which is equal to gamma and gamma will be cancelled, this is PB plus gamma ZB. This is a simple equation, this is PA is equal to PB plus gamma ZB. So he has given PB is equal to 12 and also find out PA. So this is simply PB plus gamma ZB. Only thing you need is you need to have the value of this ZB. He has not given directly. So you have ZA here and ZB, you can take a sin theta here. So 10 sin theta is 5 meters. So we have the length here, length of the pipe 10 meters here from A to B, and we have the angle here, and need to have an opposite sign is sine. So that is the datum. Only difference in this, only intelligent point in this is you need to find out this datum using the length and the angle. That is the only change. 10 sin 30 is 5 meters here. So I can use ZB is 5 and he has the gamma value. He has given 9.879 plus into 5, and also he has given PB is the 12. So 12 plus 9.879 into 5, and this is equal to 61.395 is 61.4. So the answer is 61.4. Slightly a problem which requires some intelligent way of thinking. Otherwise, it will take a lot of time and you may lose marks also that. And 13, a horizontal jet of water with its cross-section area of 0.0028 meters square. He has given the area and it has a fixed vertical plate with a velocity of 5 meters per second. The velocity of the plate is 5 meters per second. After impact, the jet spits symmetrically in a plane parallel to the plane of the plate. The force of the impact and of the jet on the plate. So this is simply rho A V square. The force exerted by the horizontal jet of water on a fixed vertical plate is given by rho A V square. It is impact of jet. The application of momentum equation rho A V square. So F is equal to rho A V square, and he has given he can take rho is 1000 Newton per meter cube. 1000 Newton per meter cube. The mass density of the water at 4 degrees centigrade is 1000. Fundamentals, fluid properties here. And the area has given 0.0028 and velocity here it is 5. So the velocity is 5 here, this is 5 square, rho A V square, this is 70. This is a simple problem. 13C. Just to know the equation and substitute the values, and we can find out the answer. But he has asked to find out Newton. So take rho in SI system only. In MK system, it is the mass density is metric slug per meter cube. In in SI system, it is only 1000 Newton per meter cube. It is required for you to know the each and every property values, known values in different systems. 14. A problem on Winchell meter. You see here the Winchell meter having a diameter of 7.5 centimeters at the throat and 15 centimeters at the enlarged end is installed in a horizontal pipeline of 15 centimeter diameter. So it has given diameters here A1 and A2. So 15 is enlarged end. So you might be confused here. This is not a D1. So 7.5 centimeters throat and 15 centimeters is for the enlarged end. So that means inlet section is 15. Slight confusion. Some other students, they may take D1 and D2 and they may be doing all these things. So here the 15 centimeters is the inlet pipe and reduce it to 7.5 centimeters here. So this is D1. So you can get A1 here pi by 4 0.15 square, pi d square by 4 A1, and A2 is 7.5 means you can take 0.075. So D1 this one, D2 this one, pi D1 square by 4 and pi D2 square by 4. A1 A2 you can get this value. And he has given the pipe carries an incompressible fluid of so and so of 30 liters per second. He has given the discharge 30 liters per second. You need to convert liters per second into meter cube per second. Most of the students are doing mistakes for conversion of liters to meter cube per second. 1 liter is equal to 10 power minus 3 meter cube. So 1 liter is equal to 1000 cc, which is equal to 1000 ml. 1000 ml is 1000 cc and 1000 is 10 power minus 6, and 1 liter is equal to 10 power minus 3 meter cube. If you remember, we have discussed the same in fundamentals of fluid properties of fluid. In one problem we have discussed about this thing, 1 liter. So the system of units, the basic fundamentals in different systems, these are all very important for solving the problem. Everything is okay, but only confusion here is liters per second. You need to convert that in meter cube per second. So 30 into 10 power minus 3, 0.03 meter cube per second, and A1, A2, and the value of H here he has given. So this is difference of pressure head measured in terms of moving fluid in between enlarged and throat of Winchell meter. This is Winchell head here, 2.45. He has straight away given H 2.45. Not necessary to convert this multiplied by S to be S1 minus 1. He has given directly in terms of moving fluid. The difference of pressure head measured in terms of moving fluid. That means not with reference to mercury is equal to 2.45. So this is 2.45. Straight away can take, not x into S to be S1 minus 1, not necessary. He has directly given the value here. Otherwise you may do this multiplied by S to be S1 minus 1, which is wrong. So he has given directly the value of H, 2.45. So he has given the 0.03 in discharge, and the areas are known, and H is directly given 2.45, and you can find out CD. CD is 0.95. Suppose if you get the value of CD 0.7, 0.6 or 1, etc., the problem is wrong. Somewhere you have gone wrong. So when you get the value of CD is equal to 0.95, that means you have taken the values correctly and you have used them appropriately in the equation, and the equation is also correct. So CD is 0.95. 50. A horizontal nozzle of 30 mm diameter discharges a steady jet of water into the atmosphere at the rate of 15 liters per second. Once again, liters per second is you can convert to meter cube per second. So 15 into 10 power minus 3. So that is 0.015. The jet impinges normal to the flat stationary hull plate closer to the nozzle end, neglecting air friction and considering the density of water. So and so the force exerted by jet in newtons. Newton means obviously you should be careful. Newton or kg force should be careful in giving units here. Simple problem here, Q is equal to AV. So Q is 0.015 and A is pi by 4 0.03 square is the area because the diameter is 30 mm. So you can take 0.03 and you can find out B here. B is 21.22 meters per second. So we have all the other values except the value of force. You can find out the force here. Force exerted by jet. So force exerted by jet, rho is 1000. Once again, be careful that the 1000 Newton per meter cube. If you take rho in MK system, it is 102 MSL per meter cube. If you take 102, the answer will be wrong. If you want to have the value in Newton, it should be 1000 Newton per meter cube, rho. And why I am stressing here is the simple mistake they are getting the equation correctly, and with the simple misunderstanding units, they are getting wrong answer. So rho you can take 1000 here into pi by 4 0.03 whole square area, and the velocity here is 21.22 square. So the velocity you know here from this equation, and finally the answer is 318.3. So you can give a 318.3 answer, Newton. The problem 16. A venturi meter having a throw diameter of 0.1 meter. Estimate the flow rate of horizontal pipe having a diameter of 0.2, and he has given D2 and D1. So D2 is 0.2 and D1 is 0.1. So pi by 4 D2 square is A2, pi by 4 D1 square is A1, and D2 is 0.2 and D1 0.1. You can get A1, A2 here. And the pressure difference of 2 meters, pressure difference of 2 meters of water head. He has given directly water head, not mercury head. Mercury head means you need to convert that 2 into S to S1 minus 1. Again, he has given in water head. You see this carefully. Otherwise, they will be using 2 into S to S1 minus 1. The problem will be wrong. They will get an upset result. So, as it is water head here, so you can take straight away 2GH. H is 2 here. And the quotient of discharge is unity. So, CD has given 1. And he has asked to find venturi meter means you know the equation here. Q is equal to CD A1 A2 by square root of A1 square minus A2 square into square root 2GH. So CD is 1 here, and pi by 4 D1 square, pi by 4 D1 square and pi by 4 D2 square, and areas here and square root 2GH. And substitute all the values, and discharge is 0.05 meter cube per second. Now 5 more questions. We will solve this also a straight pipe AB of length 10 meters. Slightly lengthy, this problem, that's why. A straight pipe AB of length 10 meters tapers from a diameter of 40 centimeters at A, 2 centimeters at B. So it has given length, he has given, and diameter is also given. The central end of the pipe is so located that the end B is 2 meters above the level of A. Liquid of specific gravity 0.9. Pipe discharge is 150 liters per second, 150 into 10 power minus 3 meter cube per second. The pressure gauge is connected A and B. That means the pressure at A and B are equal to 60 and 40. Determine the direction of flow. It has also to find out the direction of flow. So discharge you can see here, this is 150 liters per second, so 150 by 1000, so that is 0.15 meter cube per second. And this is the figure here, the length is 10 meters here, and the datum head, so here the datum is 0, ZA is 0 and ZB is 2 meters here. And the diameter here is 40 centimeters here, diameter at A is 40 and diameter B is 20 centimeters here. So at A, diameter DA is 40 centimeters and 4 meters here. And the area at A is 0.1256 meters square. So at B the diameter is 20 centimeters here, and which is equal to 0.2 meters. And find out the area, pi by 4 0.2 square, 0.034. And he has given pressure at A 60 kilonewton per meter square and 40 kilonewton per meter square. 60 kilopascals is 60 kilonewton per meter square and 40 kilopascals is 40 kilonewton per meter square. Mass density of the liquid, he has given the specific gravity 0.9, so 0.9 into 1000, so this is The value here 900 kg per meter cube, and the gamma is you can find out specific weight 0.9 to 9.81 kilonewton per meter cube. So datum A is 0 and datum ZA is 0 and ZB is 3 meters here, and you can find out the velocities here. VA is equal to Q by AB, Q is 0.15, and find out the area at A 0.1256 here, and find out the velocity at B, Q by AB, and this is the area. So you can find out V and VB, apply Bernoulli's equation. So this is HA is equal to PA by gamma plus VS plus ZA, and HA is equal to PA by W. PA, the pressure is 60 kilonewton per meter square, kilopascals, by specific weight 9.81 you can get in kilonewton per meter cube, and V square. So this is the velocity here, 0.196 is the velocity by 2z, and Z1 by 2z, Z1 is 0 here, we got 6.87, and find out head at B, that is P2 by W plus V2 square by 2g plus ZB, and the pressure at 2 is 40 kilopascals by W, and velocity V2 square by 2g, and the datum is 2 meters here, and this is equal to 7.693. So up to here everything is same. What you have done, you have applied the continuity equation and you have applied Bernoulli's equation. Nothing new on that. So the diameter you know, length you know, etc. you know. But then how will you find whether it flows from A to B or B to A? So simply find out the total head at A. If the total head at A is more than total head at B, total head at A, if it is more than total head at B, then you can say that the flow is from A to B. The node depends on datum here, because you may think that as it is in height, as the B is at high level compared to A, you may think that the flow is from B to A. Not like that. It depends on total head at A and total head at B. So total head at A is 6.87 and total head at B is 7.693. As total head at B is more than total head at A, the liquid flows from B to A. The answer is the liquid flows from B to A. That is the answer. But interesting question, use discharge equation, continuity discharge equation and Bernoulli's equation, and find out total head at A and total head at B and compare those two. So because the total head at B is more than total head at A, the flow is from B to A. Important question, 5 marks question. This is another important question, 5 marks question. So water flows through a Y joint as shown in figure. Find the horizontal and vertical components of the force acting on the joint because the flow of water. Negative losses here. Energy loss and body force. Need to consider only pressure force. Water flows through the Y joint. So this is the Y joint here as shown in figure. Find the horizontal and vertical components of the force acting on the joint because of the flow. So A1 he has given A1, P1 and V1, A1, P1 and V1, and he has given A2 and P2. P2 is 0. P2 is 0 and V2. He has also to find out what is the value of P2 and what is the value of V3 and P3. He has given A3 also. The angle is 90 here, this angle is 120. So apply Bernoulli's equation between sections 1 and 2. So this is section 1 and this is section 2. To find out the velocity here. So the datum head is same here, and P1, the pressure P1 is 150 by gamma 9.81 kilonewton per meter cube. The pressure is 150 here. So this is 1.5 to 10 power 5. If you want to have in kilonewton, this is 150 kilonewton per meter square. 150 kilonewton per meter square. So 150 by 9.81 and V1 is the velocity here. V1 velocity is 10 meters per second. The velocity here is 10 meters per second. So this is 100 by 2 into 9.81 into V2 square by 2g, the P2 by gamma, because P2 is 0. So this P2 is 0. You can have V2 square by 2z, and from that you can find out V2. So use Bernoulli's equation, Z1 and Z2. You can cancel Z1 and Z2. and you can find out V2 here. Once V2 is known, you can get Q2. Q2 is equal to A2 V2, which is equal to 2 meter cube per second. And the equation here, the discharge from Q2 is equal to Q1 plus Q3. So Q2 is equal to Q1 plus Q3. We have the value of Q2 here, and we have a Q1. He has given Q1 value. So V1, A1, you can get velocity V1 is there and A1 is there. So you can find out Q1 is equal to A1 V1. So 10 into 0.1. So that is equal to 1. So Q1 is equal to 1 from this equation A1 V1. So we have the value of Q1 here, and we have the value of 2 here, and Q2 is equal to Q1 plus Q3. You can find out Q3. And again use equation Q3 is equal to A3 V3, and you can get V3 here. So now you got V1, V2 and V3. So you have applied Bennett's equation and you have applied continuity equation. You know the values, and so that you can find out V3 also. Now it is required to find out Fx and Fy. Fx and Fy. Fx and Fy. So here, it's not 2 minutes like 2 minutes like. So Fx and Fy. So we have Fx plus, if you take here, the result of the forces here, this is P1. So P1 A1, and into angle here. So 120 means 90. 90 minus 120 is 30 here. And the balance is 60. So P1 A1 cos 60. And suppose if you see here, because the pressure is 0, so there is no other P2 A2 here because the pressure is 0. So P1 A1 cos 60 plus 0, that is the pressure here, which is equal to rho into Q2 V2 minus Q1 V1 cos 60. So you can also resolve this V1 in the direction here, x direction here. So this is Q1 Q2 V2. If Q is not constant, you can take inside. So the momentum equation, some of the forces here we have taken, and Fx is the force by the fluid on the bend. If you remember the discussion on momentum equation. So this is equal to 150 into 0.1. So the 150, so this is the value here, and 0.1. So rho here. So which is equal to rho Q into V2, rho this here, Q2 V2 minus Q1 V1 cos 60. So from that we can simplify this, and Fx is equal to 27.5 kilonewton. And similarly take Fy, this is sigma Fx, similarly sigma Fy. So which is equal to Fy take and minus P1 A1 sin 60. So you can convert this into vertical direction P1 A1, and here we have there is no the force in the vertical direction here, this is 0, and also pressure is 0, and here we have a P3 A3 here. So this is P1 A1 sin 60 and P3 A3, and also Fy, and weight he has neglected. So rho Q3 V3, so this is 150 into 0.1 and V3 and 150 into 0.1. So, and finally the value of Fy is equal to 1.34, Fy is equal to 1.34, and you can get 2.01. So this is equal to minus here, and you can get Fx and Fy with the help of these equations. So the solution here is apply Bennett's equation for finding out the velocity, and apply continuity equation for finding out the other unknown velocity. Then use, so this is the combination of continuity equation and Bennett's equation and momentum equation, all the three. That's why he has given for 5 marks. So you can find out Fx, Fy and V3 and all these things. So this is also practice, and this is the answer. So thank you. Now we have completed the fluid dynamics, and fluid dynamics is the Bennett's equation and also momentum equation, and also we have completed applications of Bennett's equation. So 3 chapters we have completed, and also solutions. I will be sending this to the organizers. They will place this information in the Anandpur website, and we have still left over 3 important chapters. One is flow through pipes, important chapter. The other chapter is flow through notches and orifice. One chapter. The other chapter is flow through. The boundary layer and lift and drag. Only 3 chapters are left over. We have 4 classes, and I'll try to cover the 3 chapters with the details along with objective questions. So thank you. Thank you for your patient hearing, and thank the organizers